afternoon, everyone. How are you doing? Have you enjoyed the conference so far? Yeah. Excellent, excellent. And I hope you've enjoyed it. You're probably a little bit tired, end of a long day. So thank you so much for choosing to attend this session. I do really appreciate it. If I do look at my fellow speakers in this slot, it looks to be all killer, no filler. But do rest assured, and this is coming from a place of pure self-interest, you have definitely made a good choice, and I hope that you enjoy this talk as much as I enjoyed writing and researching it. So we've got a lot to get through today, so I'm just going to get stuck straight in. So quick intro, my name's Adele Carpenter. I'm a software engineer at Trifork here in Amsterdam, and most of my day I spend building and maintaining Java and Kotlin applications for the educational sector. So as the title of this talk suggests, it is part 2 of a topic I have spoken about before. And has anyone ever seen part 1 of this talk, either in person or online? No one? Absolutely no problem at all. So these talks are completely standalone. You won't be missing anything at all. But if I do pique your curiosity today, you can check it out online. So while I am really proud of part 1 of this talk, and perhaps I was a little bit too ruthless in the detail that I did leave out in order to tell a story in a nice, digestible way. So I'm going to revisit that choice and provide a little bit more history and context on the to civil aviation, the study of aviation disasters, and what we can glean from that as software professionals. So first up, we're going to start with an overview of the first 50 or so years of aviation. And this always boggles my mind, because 120 years ago, we were just simple ground dwellers. And, well, now we are simple ground dwellers with flying machines. So buckle up here, because I'm going to keep the pace really, really high as we power through these first 50 years or so of aviation. So here is a bare bones timeline from 1903 to 1950 or so. So aviation as we know it started with the Wright brothers in 1903 with the first man-controlled flight. And just over 10 years later, when World War I rolled around, developments accelerated to match the new technology to the requirements of the battlefield. Between World War I and II, there was a little bit of space for a bit of fun, and we saw the first airlines, daily passenger routes, air shows, and transoceanic flights. But when the fun stopped again with World War II, developments in aviation kept accelerating. Now, most of the developments were around air-based weaponry, but we did see some more general improvements in manufacturing and in the development of the jet engine. Now, after the war, humanity had the space again to focus on commercial aviation, and we saw air traffic control grow by about 20% per year. So by the time we get to this point in the late 1940s, we have a paradigm shift in technology whose early development was catalysed by not 1 but 2 world wars, and this is followed by a rapid period of rapid adoption and growth. So what do you think is gonna happen? Disaster. Okay. So here's a summary of the causal factors of the plane crashes from 1950 until 2019. Now, I got this table from a website creatively called planecrashinfo.com. I debated whether I would recreate this table in a more aesthetic and less grainy way, but I actually kind of love it. And I know it looks like it hasn't been updated since 1996, but this website is actively administered, and the latest crash in the database is from just a couple of weeks ago. So aviation geeks are really not that different from dev geeks. We, the dev geeks, might have the slicker online tools, but the level of detail, care, and precision and obsession is basically the same on both sides. So if you were to take a Venn diagram of both communities, you'd end up with basically a circle. Now, a quick note before we do dive into the numbers here. Now, be aware this covers fatal crashes only, where at least 2 people have died. It also only looks at civil aviation, so military is not represented at all here. So now that you've had a little bit of time to digest it, even with me up here making terrible jokes, or attempting to, I hope that one thing has leapt out to you here, which is that over the decades, the most common cause of plane crashes is pilot error. Now, you may have also noticed that the breakdown by these 4 broad causes is relatively consistent, although that we can see that mechanical causes have reduced since about the 1950s and 60s. Now, worryingly, if we were to look a little closer, we might want to infer a jump in the number of crashes caused by pilot error in the 2010s. And later, we will look at a case study that hints at to why. But for now, I want to take a look at the actual numbers of these crashes. Because if we look at the actual numbers rather than the percentages, it actually tells a different and a more hopeful story. Again, with the beautiful formatting courtesy of the source website. So here we can see a peak of crashes in the 1970s at 230 with pretty remarkable attenuation after that, dropping every decade until the 2010s, where we are left with 49 crashes and 28 of them due to pilot error. Now, please bear with me for another 30 seconds. We just paint the final bit of the picture here. We can see that global fatalities per million passengers dropping consistently for decades. And we're now hovering at around 1 death per 10 million passengers. Now, climate issues aside, aviation is an incredibly safe mode of travel, and it has only trended towards safer. And this is an engineering success story that I think we could learn a lot from. Because one thing I really appreciate about the aviation industry is the deep understanding that there is rarely one cause for something. And if you read the final air crash investigation reports, and trust me, I have read more of them than I care to remember, you'll find that there is typically a list of causal factors and a list of contributing factors for a crash. Disaster is not something that just happens. Often, many systems, people, process, and mechanical have had to break down. So with that in mind, there was one big change in the late 1970s and early 80s that did drastically reduce the number of crashes attributed to pilot error. And that was the expedited introduction of crew resource management after the crash of United Airways Flight 173 in 1978. Now, I do cover that crash in more detail in part 1 of this talk, and you can check that out if you are interested. But in short, while working on an issue in resolving an issue, with the landing gear, the captain was unaware that the plane was running out of fuel. And a causal factor of this crash was breakdown of communication in the cockpit. The captain didn't ask, nor did the co-pilots assertively communicate the severity of the fuel situation. And in the end, they did run out of fuel and 10 people lost their lives. So crew resource management teaches airline crews how to make effective use of the resources available to them to ensure the safety and efficiency of flights. Now, this includes equipment, procedures, and people, both in and outside of the cockpit. Now, originally it was introduced just for pilots, but now this has been rolled out and is an important part of training for cabin and ground crew as well. And this has really been a big driver in the reduction of crashes due to pilot error. So, in the 2000s, we saw another drop in crashes attributable to pilot error as crew resource management was actually rolled out in emerging aviation markets. And the 1990s and 2000s also saw wider adoption of fly-by-wire technology and flying automation, accompanied by enhanced protections and warning systems. So if you consider this in the context of continuous improvements to maintenance procedures, training, and regulatory oversight, this really led to a period of big leaps of improvement in aviation safety. Even crashes due to the weather dropped in this period as airports gained and crews gained access to better meteorological data and training, and aircraft were fitted with advanced features like wind shear detection systems. Now, if you don't know already, wind shear is the pants browning experience of a sudden change in wind direction. So you can imagine that if you are close to the ground and you get a sudden gust of wind downwards, just how dangerous that could be. And the widespread introduction of airborne wind shear detection and alert system was a key recommendation after the crashes of Pan Am Flight 759 in 1982 and Delta Airlines Flight 191 in 1985. So in this respect, these crashes were instrumental in advancing weather-related safety in aviation. And while it certainly is true that technological advancements have been a significant driver of improvements in aviation safety, it would be remiss of me to gloss over the fact that this progress has brought with it significant challenges. And I think the discussion and appreciation of these challenges is where the real gnarly insights for software professionals lie. So fly-by-wire and its related systems has really opened the door to a lot of questions surrounding the pilot's role in flying the aircraft and the limitations of humans when it comes to understanding and interacting with automation. So fly-by-wire was first deployed on Earth with the F-16 in 1974. So traditionally, fixed-wing aircraft are controlled by a control column called a yoke, and the yoke is mechanically connected to the flight control surfaces of the aircraft. So when the pilot pulls the yoke back, this is a direct input on a cable which moves the elevators up, driving the tail down and therefore the nose up. And the key point here is that there is a cable or rod running from the cockpit to the tail and the other flight control surfaces. So in fly-by-wire, though, the flight control computer accepts pilot input to the controls and manipulates the control surface in such a way as to produce the pilot's desired result. So essentially, the flight computer acts as a middleman for the pilot's instructions, a much lighter, smarter, and more opinionated middleman than traditional cables and rods, delivering the instructions by wire. So this middleman can and does provide protections to ensure that the aircraft stays within its safe flight parameters. So if the pilot is trying to pitch the nose so far up that the plane will lose lift and enter a stall, the computer will be like, nah, I don't reckon, and will make a much smaller and safer adjustment to the flight control surfaces. So in the words of the early F-16 pilots, you don't fly an F-16, it flies you. So moving back now to the commercial realm, 1988 saw the introduction or the launch of the Airbus A320, which was the first airliner with fully digital fly-by-wire controls. And it was also a key moment in what has become somewhat diverging philosophies of Airbus and Boeing with respect to automation. So Airbus's stance is that automation should allow the pilot to use the safe flight envelope to its fullest extent. So the flight envelope is basically the safe operating limits of the aircraft, although this can vary based on weight, speed, and altitude, amongst other things. So at a certain weight and speed, for example, there is a safe range of altitude. And it's also where the expression in English, pushing the envelope, comes from, to mean pushing the limits of a situation. And the flight computers on Airbus follow a series of laws that offer various levels of protection. And a protection is basically a nah, I don't reckon response from the computer. So these laws are called normal, alternate, and direct law. And in normal law, you have the most protections, and in direct law, you have the least. And I think it's a very telling design decision from Airbus that is actually not possible for the pilot to decide which law they wish to operate under, and that is always determined by the aircraft. And so the only way that I can think to explain this is to say that Airbus takes a computer-centric approach. Boeing, on the other hand, has traditionally taken a much more pilot-centric approach. Now, they did in 1994 introduce the 777, which is fly-by-wire, and later the 787 or Dreamliner. However, their highest-selling aircraft, the 737, decidedly has mechanical controls. And a quick nod to the elephant of the room called Max, because we have seen some deviation from that approach recently with the introduction of MCAS on the 737 MAX 8, but that is a bit of a special case and that is worthy of its own talk. You're in luck though, because there is a talk about the MAX 8 by a man called Kyle Kotowick. I saw that talk last year and I highly recommend that you do see it. He has been giving that talk for a little while now, so you should be able to find it online. No worries at all. So in any case, I'm not in a position to make a claim about which philosophy is better, pilot-centric or computer-centric, if one is at all. However, I find the fact that the two largest aircraft manufacturers, despite traditionally putting the same priority on aviation safety, have taken two very different approaches to achieving it. Because indeed, what are the appropriate roles of human and machine when it comes to machine-assisted decision-making? Because we're facing this question right now with the introduction and growing plethora of AI assistance tools. And there's one crash that I think sums up these themes really quite well, and I'm going to share it with you in a storytelling format. Now, I do warn you that it is quite heavy, and it's also, in aviation terms, relatively recent. This is the heaviest part of the talk, but it does set us up for a nice discussion afterwards. So just to break the suspense a little bit while I take a sip of water, the flight is Air France 447, which crashed into the Atlantic Ocean on June 1st, 2009, as it was returning to Paris from Rio de Janeiro. So, and it's just a quick little warning as well to just prepare your eyes a little bit because we're just about to enter dark mode. So, it's June 1st, 2009. Air France first officers Daniel Robert and Pierre-Cédric Bonin are in the cockpit of the Airbus A330 over the mid-Atlantic Ocean. Bonin, the less experienced of the two pilots, is the pilot flying in the right-hand seat, and Robert is the pilot not flying or the pilot monitoring in the left-hand seat, the captain seat. So wait, where's the captain, you might wonder? Now, as this is a 14-hour flight from Rio to Paris, the allowed duty time for pilots of 10 hours will be exceeded. So in order to complete the flight and to manage fatigue of the crew, the three pilots rotate so that one of them can get some rest and then remain alert while they actually are in the cockpit. So Captain Dubois has just stepped out for his rest. Nothing out of the ordinary here. However, Bonin is feeling a little uneasy. He's flying through the intertropical convergence zone in June, and as is common at this time of year, he's experiencing some light turbulence as he flies through a layer of cloud. Now, he had discussed the weather with the captain just before Dubois took his rest, and he'd proposed a couple of small adjustments that they could make to the flight path to potentially avoid the worst of it. But Captain Dubois was not particularly concerned, and the proposed adjustments also carry some risk. And Bonin and Robert notice some ice crystals in the cloud layer and turn on the anti-icing system. Less than 3 minutes later, an alarm sounds. The autopilot has disconnected. I have the controls, says Bonin. The plane rolls from side to side a little as Bonin settles into flying the plane manually. He pitches the nose up. We haven't got a good indication on speed, he says. The autopilot has disengaged because the flight computer can't make sense of the data, the conflicting airspeed data that it is getting. The data is bad because the airspeed sensors are clogged with ice crystals. Alternate law, protection's low, says Robert. In alternate law, there is still some support from the flight computer, but critically, there is no anti-stall protection. Not long after Bonin takes the controls, the stall warning sounds. Now, the stall warning is designed to be as intrusive as possible. So you can think of the loudest crickets that you have ever heard and multiply it by 10, and that's on top of a continuous C-chord master warning, as well as multiple visual alerts. It is pure sensory overload. Robert adds to what must be overwhelming noise in the cockpit. Watch your speed, watch your speed. Okay, I'm going back down, says Bonin. According to all three, you're going up, so go back down. Bonin reduces his nose-up input and thrust, and the stall warning temporarily stops, although there are still several other warnings demanding their attention. The pilots have control of the aeroplane again, yet confusion remains. Unbeknownst to them, the airspeed indicators sensors are now ice-free, and all of the avionics are functioning normally again, although there is still some curious behaviour from some of the instruments. They still don't really have a full grasp of the situation. Robert focuses his attention on summoning the captain. Damn it, where is he? The stall warning starts again. I'm in toga, right? Says Bonin. Toga is short for takeoff and go around, and this setting provides the maximum thrust needed for the plane to take off with the nose pitched up. Now, it's designed to be used at a lower altitude where the air is heavier. So this statement hints that Bonin has, to quote the investigation report directly, built an erroneous representation of the aeroplane's flight model. And the fact that his actions are not resolving the warning deepens his mistrust of what the aeroplane is telling him. And he may be further emboldened by the fact that the A330 does carry robust anti-stall features. Anti-stall features that are not available to him in the flight computer state of alternate law. I don't have control of the aeroplane anymore now, exclaims Bonin. Controls to the left, asserts Robert. 8 seconds later, Captain Dubois enters the cockpit. What are you doing? What's happening? I don't know what's happening, says Robert. We're losing control of the aeroplane, confirms Bonin. Now, over the next 2.5 minutes, the three pilots try to understand and resolve the situation. Captain Dubois recognises that they're in a stall, and Robert pushes the nose down to try and gain airflow over the wings. More airflow, more lift. But they cannot regain control of the aeroplane. When they get dangerously close to the sea, Robert reverses inputs by pulling back and saying, climb, 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 climb. Chillingly, Bonin responds, but I've been nose up for a while. Captain Dubois pleads, no, don't climb. Give the controls to me, says Robert. Go ahead, you have the controls, we're still in toga, yeah? Replies Bonin. Robert spends the next 35 seconds trying to recover the aeroplane, but it is far too late. Moments later, Bonin exclaims, we're going to crash, this can't be true. And the cockpit voice recording ends along with 228 lives. So I've read the transcript of that flight many, many times, and it still sends a chill down my spine every single time that I read it. Now, for obvious reasons, the real recording has not been released to the public, but I can just imagine the investigators sitting there listening to it, it's like dumbfounded. And it's easy to blame the pilots for this crash, and many people have, including the press and the courts. And to say that they are not at all responsible for the crash would also be incorrect. But as someone who did not lose a loved one in this disaster, I have the luxury of being able to avoid the blame game, and I can instead focus on what we can learn. And do you see here in the subtitle the implication that the pilots were shirking their responsibilities and sleeping on the job, a sleep mandated by safety requirements? Yeah, classic tabloid journalism. Anyway, I digress. So Air France 447 highlights something that I don't think we think about enough as software professionals, and that is how we as humans interact with complex systems, particularly those with a lot of redundancy. Because there's a tendency to think that outside of cost considerations, more redundancy is better. And in safety critical systems in particular, you're willing to take on those extra costs in order to have that extra safety or fallback. And even in non-critical systems, there is a level of expected redundancy. You know, the classic example being backups and having your application running in multiple regions or data centers, or running your database or message broker as a cluster. Indeed, in my team at Trifork, we run our own cluster of 3 nodes of our message broker, RabbitMQ, because 3, of course, is the magical minimum number for redundancy. And recently, we encountered a situation that caught us a bit by surprise and resulted in 8 minutes of downtime of our main application during a busy period. So, show of hands if you're using RabbitMQ in production. There are 2 people here that are lying, at least. So see if you can figure out what's happening as I tell the story. So just as you would see in the cockpit, we started receiving alerts about an unexpected state. We had a growing number of messages of 2 of our production queues, in addition to disks that were getting dangerously full. And the number of messages in 2 of the queues was around 600,000 each, which was high, but not unexpected during a busy period. However, the rapidly shrinking disk space was concerning and the message throughput was slow. So we decided that a relatively low-risk course of action would be to restart one of the affected applications listening on one of the queues. Unfortunately, though, that didn't resolve the issue. So after some back and forth in the team and with the disk getting ever more full, we decided to take the secondary RabbitMQ server offline and bring it back with extended disk space. And at first, this seemed to go really, really well. We took the node offline without a problem, and the application was still limping along, serving requests with fewer nodes. But there was a key part of this redundancy model that we didn't understand. Because these classic queues were still very, very large, in total over 1 million messages, when we reattached the node to the cluster, the node started to sync itself to the queue. Yeah, basically stopping time while it copied 1 million messages, and all we could do was wait. So during what felt like the longest 8 minutes of my life, no messages could be consumed at all, and as such, our main application was unavailable to our users. So I saw someone nodding. You knew what was going to happen? Yeah, all right. And is that because it's happened to you before, or because you're the only developer on the planet that reads documentation? So look, this is not a perfect example, but it does show the perils of interaction with complexity and redundancy when under pressure. So probably somebody on the team should have known about the sync time on such a big queue, but you know, once set up, these queues just kind of work. So back to the Airbus, and here's the schematic of the systems involved in providing aerodynamic and inertial parameter data to the pilots of the A330. So ADIRU is short for Air Data Inertial Reference Unit, and you might recall from the first part of the Air France 447 story that the autopilot disconnected due to conflicting airspeed data. And the air data part of the ADIRU is most notably responsible for providing calibrated airspeed and Mach data to the pilots. And if you're thinking, wait, isn't Mach speed too? Well, yes, you're right. Mach is presented as a fraction of the speed of sound, and calibrated airspeed is presented in knots. And I'm oversimplifying a lot here, but above about 28,000 feet, Mach actually becomes the more important measure of airspeed. Now, the inertial part of the ADIRU provides data such as the ground speed and the attitude or pitch, so the number of degrees that the nose is pitched up or down relative to the ground. So you can see here on the left and the right side the physical sensors that are providing data to the ADIRU. And without getting too bogged down here in specifics, the airspeed data is calculated from the static and the total air pressure. And there are 6 static air pressure sensors on an A330. And the total air pressure is measured by something called a pitot probe, which is a small probe that sticks out the side of the fuselage. And an A330 has 3 pitot probes circled in green here. Now, as you can see here, the data from Pitot 1 feeds the captain's flight display. Highlight that one for you. Pitot 2 feeds the co-pilot's flight display, and Pitot 3 feeds the standby flight display. Now, you can also see something here called ISIS, which is an unfortunate name, I know, especially for something on an aircraft. But it is the integrated standby instrument system. Now, this is designed to serve as a backup in case of the failure of one of the standard flight displays. So you can forget turtles here. It is redundancies all the way down. Because we have redundancy of data, given that we have multiple sensors measuring the same thing, we have static redundancy of the 3 ADRUs, where an error in one system can be outvoted by the other 2. We have the redundancy on top of those 3 flight display systems with an external computer system that integrates information from a variety of sources. And if you got to this point now and you're feeling overwhelmed, confused, unsure, or simply bored right now, well, then you already understand the point that I'm trying to make, which is that redundant systems do not operate in isolation. When they work, they're great. But when they fail hard, often in unexpected ways. And what often you'll find at the other end are some humans under immense pressure, not only to figure out what is happening, but also to save the day. And in the case of Air France 447, the cascade of unfortunate events started with a loss of reliable airspeed information due to the pitot probes icing over in the absence of the captain. The autopilot could not make sense of the conflicting airspeed data it was getting, so it disconnected. Let the humans figure it out. The aeroplane displayed an abundance of alerts and messages to the co-pilots who had not encountered this situation before, not even in the simulator. And to make matters worse, many of these messages were about the consequences of the problem rather than about the origin of the problem. And unable to make sense of what was being presented to them, the pilots failed to diagnose the situation correctly and apply the appropriate checklist. Now, under stress and possibly suffering from the startle effect and possibly reacting to the intermittent appearance of the crossbars on his display, Bonin pitched the nose up. And he had little practice manually flying the plane at altitude, as he was used to the A330's anti-stall protections. But the anti-stall protection was gone once the flight computer shifted into alternate law. And this was a fact that Bonin was expected to recall within seconds. In fact, the civil regulator of the US, the FAA, assumes pilots can recall such pertinent information within 3 seconds. So, tragically, the attempts of Robert to push the nose down to gain speed to recover the stall proved futile due to the design of the cockpit and the controls and the fact that it was dark. Robert could not see that Bonin's side stick was being pulled back while he was trying to push down. So the conflicting inputs of the pilots, one nose up and one nose down, effectively cancelled each other out and added even more confusion to the situation. And so when Bonin finally exclaims, "But I've been nose up for a while," that was when the penny dropped, but it was just far too late. And Air France 447 is basically the poster child for automation gone wrong, and the media certainly had a field day with this narrative. But the more interesting and less tabloid-worthy discussion for me is, how do we design more human-centric systems in a digital world? Not just for users, but for ourselves as developers. Because I really dislike this approach of, oh, well, if the unexpected happens, say, I don't know, and hand it back to the users. Like maybe you can get away with that with simple systems, but as the system gets a lot more complex and you're actually demanding a lot from your users. So at best, your user does get annoyed, but does in fact try again later. And at worst, you have a plane falling out of the sky. Somewhere in the middle, there's me holding my breath for 8 minutes while a new node syncs a million messages while it reconnects to the cluster. Somewhere next to me, there's you having a mini meltdown because your Slack is blowing up and your exquisite dashboards have disintegrated into an amber red mess. And in the corner, there's Pete having a great time with his headphones on and his alerts muted because, the alerts don't usually mean anything anyway. And so in order to start thinking about human-centric design, you've got to understand some simple features of humanity, or depending on who you ask, bugs of humanity. And aviation has certainly encountered most of them. So the first is that we have a limited working memory. So are you already familiar with the concept of cognitive load? Yeah. Okay, so just quickly, cognitive load refers to how much of our working memory is required for a task. Now, you may have heard that our working memory can hold 5 to 9 chunks of novel information. That's correct. But the number that shocked me is that only 2 to 4 of those chunks can actually be thought about or worked on at once. But the cool part about this is that this limit only applies to truly novel information, not information that you already have in your long-term memory. So for pilots, this highlights even further the importance of relevant training and experience to free up as much working memory as possible for truly novel information. And as developers, we can strive to make our systems, the way people interact with our systems, as consistent as possible. So consistency over correctness is not a dead concept at all. So Copa Airlines Flight 201 highlights the importance of consistency in human-centric design even further. So in 1992, a Boeing 737 crashed in Darien Gap, a region of almost impenetrable jungle in Panama. And despite intense challenges of the terrain, investigators were able to actually piece together the flight data recorder and collect the bulk of the wreckage. Now, a key piece of the puzzle is the data from the captain's vertical gyro. So the gyro is the data source for the attitude indicator here, which I think is the instrument most people can recognize and associate with flying. Now, this one is similar to the one found on Copa 201, and it shows the plane in relation to the horizon, and it's very, very difficult to fly with that one, especially in the dark. So given that it's so critical, some very smart engineers built some redundancy in. So similar to we saw with the A330 and the airspeed data, there is a gyro on the captain's side that feeds the captain's display and one on the right side to feed the co-pilot's display. And there's also an auxiliary gyro to feed a standby display. And if you identify an issue with the data of one of the gyros, for example, the captain's gyro, then there is a switch where you can set the data source for both displays to be the co-pilot's gyro, like this. So also similar to what we saw with Air France 447, Flight 201 starts receiving bad data, which causes the autopilot to disconnect. And this time, the faulty data source is from the captain's gyro. So in the dark, the pilots need to manage flying the plane with a broken attitude indicator. And the investigators can only be shocked because the flight data recorder actually tells a terrifying story of the pilots repeatedly reacting to bad data until the plane falls out of the sky. Why didn't they just switch the data source? So here is how the switch appeared when it was pulled from the wreckage. Now it says both on VG1 or vertical gyro 1. So this means that the pilots had identified that they were in fact getting bad data, but then they pointed both displays to the bad data source. Like, what on earth were they thinking? So let me show you the same switch as it was installed in the simulator that the pilots were trained on. Now, just leave to the side for a second that it's a different style of switch altogether. But I'm not sure if you can see it, but in the simulator, left means give the captain the auxiliary data. And in the plane, left means switch the co-pilot to the pilot's bad data. Now, this is deadly UX if you're ever going to see it. And it's about the most extreme example you're ever going to see of consistency over correctness. So moving on to the second bug of humanity now, which is that we have a blind spot for our assumptions. So in 1989, British Midlands Flight 92 crashed while attempting an emergency landing. The first sign of trouble in the cockpit was a loud pounding noise and a severe vibration. In the cabin, smoke poured in, and some passengers could see sparks coming from the left engine. And whilst the pilots were very experienced on this aircraft type, the 737, they only had about 76 hours combined on this version, the 737-400. Now, in previous versions of the 737, the right air conditioning system receives what's called bleed air from the right engine as it supplies air to the cabin, and the left does the same for the cockpit. However, on this newer version of the 737, the air from the left and the right is mixed before re-entering the aircraft. Now, the captain, relying on his experiences, senses the smoke coming forward from the cabin and assumes that the fault is with the right engine. And based on this shared assumption, he and the co-pilot power down the engine on the right. And unfortunately, as bad luck would have it, at this exact same moment that they power it down, the auto throttle disengaged, reducing fuel flow to the left engine. So as a result of this, the fire weakened and the smell of smoke subsided, which actually seemed to confirm to the pilots that they had made the right choice. But when they start the approach for the emergency landing, they increase the thrust, which then grows the fire to the extent that it kills the left engine entirely. And by this point, they are just traveling far too slowly in order to restart the good engine, and they crash right next to the motorway. Now, I have a little bit more to say about the Midlands crash, but before I do, I want to introduce the next bug of humanity that we'll be discussing today, which is that we do irrational things. Now, despite heavy protests to the contrary, rational people do irrational things. Yes, even developers, and yes, especially users. Now, British Midlands was one of two crashes in Britain in the 80s that was pivotal in improving aviation safety and the survival rate, of survivable crashes. And no, this is not just because everybody got a lecture on verifying their assumptions before acting, although that would be useful for most people. I'm sure you can think of a colleague already who could use that lecture. So, of the 126 passengers and crew on board Midlands Flight 92, 79 people survived, with 74 of them suffering injuries. And by examining the injuries and the aircraft, a number of recommendations were made relating to the aircraft itself, such as improvements in seat floor and overhead bin design. There are also some changes made to the recommended brace position and the restraints of young children. However, the survivors of the Midlands crash had actually already benefited from the 1985 Manchester airport disaster, which happened only 4 years earlier. So in this crash, an engine failure during takeoff generated a fire. The takeoff was aborted and the captain ordered an evacuation. They were on the runway and the slides came out. And of the 137 passengers and crew on this flight, 55 died, remembering they were still on the ground, mostly from smoke inhalation as they attempted to rush, climb, fight and squeeze their way out of the emergency exits. So the Manchester airport disaster forced manufacturers to consider the behaviour of a group of humans facing death, behaviour which in most other situations would be considered completely irrational. So these changes included making it easier to find the exit by installing the strip lighting in the aisles, creating more space for exiting the aircraft by removing a seat at the overwing exits and widening the entry to the galley. So the galley might otherwise be known as the place where the terrible coffee is made. Installing fire suppression systems in the cabin, and the introduction of less flammable materials for things like seat cushions and carpets. So, only a few small changes, smash it out in a weekend. And for airlines, the changes included spreading crew of different experience levels throughout the cabin and a pre-flight safety briefing for passengers in the exit row. So that briefing in the exit row really did come out of a real case, and people actually died. And that's how we got the need for that safety briefing. So maybe you might want to listen to it the next time you get one. It's not just free leg room that you're getting. So, digging down into an individual level here, irrational choice is often driven by bias, emotion, and stress. So, in the final report for Air France 447, investigators mentioned that the crew acted irrationally in response to the anti-stall warning, probably due to the startle effect. Now, ongoing training is often well known to the crews, blunting their ability to act in a measured way to the truly unexpected. But I think the bigger point here is about the role of stress in your user's behaviour. Have a think about the stress that your user could be experiencing, for example, noisy environments or a poor internet connection. How can you make it easier for them to interact with your application under those stressful circumstances? And the last bug/feature of humanity I'd like to mention today is simply that we get used to things. So, as was the case with Pete and his muted alerts, repeat applications of a stimulus tend to result in a decreased response. Now, in psychology, this is called habituation. So, if the alerting is too eager, eventually you'll start to ignore the alerts, which will put you in the same position as if you had no alerts. And a manifestation of getting used to things is simply going through the motions. Even if something does have a high risk of going wrong, if you do it often enough, you can become complacent. So in 1988, Delta Airlines Flight 1141 crashed shortly after takeoff because the flaps were not deployed. So these things here. And as you can see, the flaps extend out the back of the wing during takeoff and landing. And what they do is they extend the surface area of the wing so it can generate more lift while it's moving more slowly. And it's a pretty crucial part of the takeoff procedure. So in the cockpit recording, the pilots can be heard chatting while going through the pre-flight checklist. And while the pilots both announce the deployment of the flaps, the sound of the flap lever moving into position actually cannot be heard in the background. And examination of the wreckage confirms this finding. However, the pilots who had survived, they were in pure disbelief, absolutely astonished. They were certain that they had deployed the flaps. And the absolute kicker in this case is that the aircraft, a Boeing 727, did have a takeoff warning system installed. And this system provides an audible warning to the pilots when the aircraft is not ready for takeoff. So it literally yells at you when you try to take off without the flaps deployed. In this case, the switch that operated the takeoff warning system had been modified to prevent nuisance activations during aircraft taxiing. So it wasn't active and it didn't yell at them. So I think we're going to not quite have enough time for this story, but I will be sticking around afterwards. This is basically, if you ask the internet why airplane windows round, you'll get an answer to do with this aircraft. We're going to... Look, do you want to stay a couple more minutes, or do you want to... All right, I'll tell you. Okay, let's go. So I did promise you in the abstract discussion of project failures and wrong incentives. And if I'm honest, when I promised you that, I did have this story in mind. But you got to imagine my disappointment when I find out it's not true. So this is the de Havilland Comet 1, the world's first commercial passenger jet. And if you do ask the internet why aeroplane windows round, they'll say, because of the comet. We tried that and it crashed because stress at the corners of the square windows. So let's have a little bit of a look there. All right, they're square, okay. So the story gets better because apparently it was the manager that suggested that the windows be square so as to separate air travel from the round portholes of sea travel. And so because the ego-driven manager said so, and with centres in place that favoured not rocking the boat over prioritising safety, we got square windows and disaster. All entirely believable and relatable, but all mostly untrue. The Comet did unfortunately suffer from structural fatigue issues in the fuselage, and if I've been doing my job correctly today and holding your attention, you should already know that there's almost never only one reason for a failure, and of course this case is no different. But if you did have to go back to a choice zero, so to speak, it was the decision to use a particular type of engine, an engine which was severely underpowered, which required the design of an ultralight fuselage, which proved susceptible to structural fatigue, which was actually a phenomenon we didn't understand well at the time. So, we're at the point now where I make some closing remarks and I put today's talk into a neat little package, and the part where I give you a list of takeaways that you can take a picture of. But before I do that, I want to acknowledge that I've probably given you more questions than answers today, and that's totally fine by me. So I want you to take the list of takeaways that I'm giving you with a grain of salt, and if there's something else that really resonated with you today, just take that and run with it. And if you do see me after the session at the gathering there, I'd love to hear your take. But for now, this is what I hope you got out of the session. So first, rapid adoption of a new technology will always have problems, but it's the way that we approach these problems that matters. As the technology matures, the human element becomes even more important. Focus shifts from making the technology better to understanding the users better. More redundancy is not always the best idea. It's important to weigh the extra safety and reliability of the system itself with the cognitive load put on users to understand and interact with the system. Users is a wider definition than you think. Start thinking of yourself as a user of the system that you build and maintain. See where that gets you. Lastly, the humans that interact with your system have significant shortcomings simply because we are human. Learn to work with it, not against it. My name is Adele, and thank you so much for your time. Please don't forget to rate this session via the app, and the slides are available on the QR code. Thank you.